To analyze the data, you will need some quantitative characterization of your peaks, and that means finding the peak position and peak width, sometimes peak intensities or peak areas. For that, to determine them properly, you will need to perform fitting, and you can access this menu using Analysis menu, Peaks and Baseline, Peak Analyzer, Open Dialog. In this menu, you select the Fit Peak option. Next, and you can see that our spectrum isn't exactly at 0, to be honest. It will not be good for the fitting afterwards. So I'm going to set 0.1 baseline. With this baseline, we now need to add the peaks, and we can let the software find them automatically, but sometimes it overdoes it. So I will disable this function and clear the peaks. Now I will add them manually. We have 3 obvious candidates, and we can fit them by pressing next and going to fit control. In fit control, important parameter is selecting the function of the line shape of the fit. Gaussian is the default function, and you would use it if you have an amorphous material with a lot of scattering. Lorentz is the shape that corresponds to the oscillations of a harmonic oscillator. That means if you have high quality oscillations of the molecule bonds or phonons. Voigt function is kind of a mix between Gaussian and Lorentzian, and you can use it as well if you have some intermediate case. It's often hard to know which case exactly you have, so you follow line shape that fits best. Let's start with Lorentzian, that is the most common in Raman fitting. And now I press fit to let the software run it. To understand whether the fit is good, I look at the red line. That is the sum of the peaks that are proposed, of the blue peaks that are fitted. And I look how well it follows our original data. There are a lot of discrepancies. Apart from the fact that it doesn't follow the baseline, there are also these shoulders where it doesn't match, and clearly this shape has nothing to do with Gaussian shape. There are probably 2 peaks. So I'm going to add a few peaks. And I will also change the function to Gaussian because these peaks are rather wide, what tells me there is probably a lot of scattering. Now look at this fit. This peak, it's still fitted with 1 only, and the second peak just became horizontal line, so just to correct for the baseline. Then we have this fit that is now way better. You can see how it accounts for the asymmetric shape of this vibration. Now I can add 1 more peak, and keep in mind that if I am to analyze it, this peak that has extremely high width and low intensity cannot be taken into account. It's just correcting for the baseline. Let's see if it improves our fit now. And it barely has any effect. But I'm still not quite happy with that, so I'm going to try Lorentzian function. Fit. And you see that it failed to fit it with Lorentzian function. It doesn't always mean that it's impossible, but in this case, it invoked some negative intensity peaks. You can disable it also in fit control, but in this case, the Gaussian works well. Okay, and now refitting is sometimes very helpful because the software iterates from the positions where the peaks are. So if you have already some peak positions, it can go you astray. Sometimes it's convenient to just go back, move the peaks around, and let it fit in you to improve the convergence of the algorithm. Now I'm pretty happy with this fit. It's a bit imperfect here, but this will not have high impact on my analysis. So I'm pressing finish. And Origin offers me to generate a report sheet. The report sheet is added to your data sheet as an extra tab. Here you have the report, but also the curve, each of the peak properties, and baseline data, that is just 0.1. Let's look at the report. For each of the peaks inserted, we have 3 key parameters. That is the position of the peak, its area, and its width. Here you have the error bars. These are also very important parameters. For these white peaks, even for them, 1.7 is a rather high error bar. You will be happy if your error bar is 0.1. That's typical for sharp peaks with low noise. But if the peaks are convoluted, that means they're very close to each other and it's hard to separate the effects, you will see values something like 1 or 2 reciprocal centimeters, like you see in some cases here. And here you even have a negative peak with extremely high width. That's again the one compensating for the background. This peak we just don't take into account. And we have the 6 peaks, these 3 and these 3 that do make sense. We will use these values for X and area to compare different spectra. Now I'm also going to check this sheet. The red line is the sum. You can look at the residue during the fitting process, and you will discover whether the fit is actually good or there is something important you are missing. And you can see the residue here in the bottom. You can see that it's rather homogeneous within 0.05, that's 5%, and that's the error bar you would be aiming at. That's it. Now we have the data to compare the different peaks.